Zoom recording. All right. Sorry. Thank you very much. We talked about conversions mostly. You can find it on Google. I did post a couple pages, one sheet of trig review, handy formulas. You might want to document that, and a quick cheat sheet on conversions. I had one taped to my computer for the longest time. It just comes in so handy. I still haven't been able to memorize how many acres or how many square feet there are in an acre. I know ballpark. It's just one of those things that kind of throws me. So I look it up every time. We talked about significant digits. How do we figure out what the significant digits are? Depends on the mathematical situation that we're in. Are we adding numbers? Are we multiplying or dividing numbers? There's a good explanation in the textbook. Again, Google. And then the homework assignment. Was everybody able to access the homework and get it turned in? I saw that there were about 15 submittals. Seeing a thumb, so that's good. Couple of them. All right. Were there any questions or concerns on that? Okay. All right. So moving right along. There's our quiz. We're going to use Canvas. Resubmit as often until the time is up, 20-minute time limit. So jumping right in, let's talk about the objectives of surveying. And here's where I have to get a little creative. Give me a moment. I swear, one day I will get my stuff together. But to quote Braveheart, today is not that day. Sorry. Let's see, which one am I looking for? Oops, not that one. Come on. Oh, hell. Screen sharing. Love it. All right. So what are we looking for when we're doing a survey? What kind of things do we want to document when this comes up?
Topography, so like elevation.
Okay. So why would we need the topography? Why do we need the elevations? In this first example that pops up, one of the things that we see is proximity to other structures, to other monuments. So that's one thing that we would be looking for, right? Example I gave last week or 2 weeks ago, gosh, 2 weeks ago already. Where's my property line? What do I own? Where does my property stop? What did I pay for? So that's one of the things that we would want to look at, is look at property lines, boundary surveys. Can I put that pool in? Where's my drainage supposed to go that my neighbor is infringing upon? And one question that I got asked not long ago, and I thought it was really a really good question. Why do engineers pick that location to put the interchange or to put the bridge? You know, there might be a more direct path. There might be a cleaner way of going across a gorge. And yet, for some reason, the engineers have brought you up one side. You don't cross for another couple miles. Then you cut across and come back down. Is it because it's narrower there? Did we have better soil conditions? Why did we pick that area? And that's one of the things that we need to look at with surveying. Do we have room for such an interchange as that? That's actually not terrible. Looks like it's down in Texas or something. All those frontage streets where you can drive for miles and miles on the frontage road. So those are the things that we look for. Those are the reasons we need to create surveys. We need to go out and figure out where are our boundaries, what are our limits, what do we have to work with. So we talk about two different types of surveys, and these are horrible screenshots, but really they are the best that I could find. And I've also inherited most of these images from previous lectures, previous instructors. So the thing that we're going to look at here is the difference between geodetic and plane surveys. Okay. So geodetic geodetic is based on the curvature of the Earth's surface. So once you get up to about 50,000 feet, then you start seeing the curvature of the Earth. Beyond that, most of the time, if we look out, we're not being affected by that arc, by that dip in the spherical shape of the planet, right? So we do take that into consideration. Any two stations, the distance between them is considered to be a curved line, the radii being the dimensions of the planet. Any triangles, instead of being a nice flat triangle, they're suddenly curved. They're going to have an arc shape to it. So only if we're looking at very large areas, 250 square kilometers. All right, that's pretty big. Basically, we're saying about 247 acres. That's a lot of square feet. Okay? But if you're a farmer and you're out planting a field and you need to grade your site to drain, you might want to take that into consideration. You might need to think about how you have that arc there, how the end is going to be different. You have to adjust for those elevations. Most of the time, we will look at plane surveys where you have a horizontal plane, right? We're going to be dealing in those, basically those two dimensions. So we're looking at it as a flat surface. The flat earthers love this. We have to ignore the curvature of the Earth, mainly because it makes the math hard. It's not a big enough difference over the course of the next quarter mile, right? It's much bigger distances where we will see that differentiation. We're dealing with straight lines. We love straight lines. Those curved lines are a little harder to figure out. Any triangle is going to be a nice flat plane as well. We get to deal with standard geometric mathematical formulas. We get to deal with trigonometry in a very confined realm, right? We don't have to go deep into the math or the thought process. It's kind of nice. We're just dumb dirt jockeys. So smaller areas, this is great for, right? So if I have 40 acres that I need to go out and survey, I'm going to put in a subdivision. I don't need to account for the curvature of the Earth. I can deal with nice straight lines, flat surfaces. Unfortunately, the Earth is not a perfect sphere, right? Oops, getting a little ahead of myself here. So they call it an oblate spheroid. We're really never going to use this. We deal with such small areas in general. Yeah, there's these master plan communities, these huge areas going across. Most of the time, we're just going to deal with a plane survey. So one thing you'll hear periodically, I don't know if you've heard it before, as the crow flies. So apparently, in addition to learning people's faces and having groups of them being called a murder, which is fascinating, as the crow flies, meaning obstructions are not an issue. Variations in terrain are not an issue. They don't have to go to the corner, stop at the stop sign, and then turn left. A crow is going to fly in a straight line from point A to point B. That's what we do when we talk about plane surveys. We don't look at that variation. We take this sphere, like the Earth, where we look at a latitude and a longitudinal coordinate system, and that's that phi and the lambda. Is that, yeah, that's lambda, I think. It's been a while since I had to deal with my Greek alphabet. We take it, we flatten it. Then we're dealing in XY coordinates, okay? From there, we can differentiate our points and our places. Who would use geodetic surveys, though? Who deals in such large scales? Whereas most of us we're dealing on a much less than 250 acres, right? Who would do some kind of large scale survey that we would have to take into account the curvature? When I sip, you can talk. Roads, dams, yeah. Yeah, that can be an issue. Dams, again, we're not always dealing with that large of an area, but some of the areas that we would be looking at, some of the things that we want to see, NOAA, what's happening with the Earth? What are the tectonic plates doing? What's happening out in our atmosphere that's impacted by that kind of a shape? Another service that might use geodetic surveys, USGS, the Geological Survey. So if they are mapping out something like the San Andreas Fault, running from Southern California all the way up the state, up through Hayward and San Francisco, they're going to want to take into account the curvature. They're dealing with tremendous distances in that respect. And then there's this one. This I thought was interesting. Roads, dams, mines, those we're dealing with huge areas, massive areas. We need to know the strata of the Earth. We need to know what material we're looking for, and that's going to vary. How far down do I go? Is it a flat layer or is it going to be curved? So where am I going? What am I doing with it? If I'm talking pretty big scale, NOAA, USGS, Army Corps of Engineers, mining facilities. The deepest mine in the world is located right in Salt Lake City, just outside of town. It's amazing. It's like 2.5 miles deep, or 2.5 kilometers, something like that. It's huge, impressive structure. Okay, so the ones that set the global positioning, the agencies and the entities that do that kind of a work, they're going to go with the geodetic surveys. Google Earth, they're going to use more of a geodetic process. We're going to stick with plane surveys. Okay. You might come across some problems later on. We might introduce what you have to do in the event you're dealing on a much bigger scale, but for the most part, most of what we see and what we will deal with is going to be the nice, flat, linear, simple stuff, okay? Because I don't know about you, I'm looking at A through G through N on this, and if we were to take that triangle, that pie shape out of the sphere, the summation of those angles is going to end up being 270 degrees. Well, all of my math says the summation of angles of a triangle is 180 degrees. So right there, you've blown my mind, you've lost me. So we want to be sure we are clear about which sides we're looking at. What are we looking for? Okay. All right. This was an interesting graphic that I came across, right? If we look at how are measurements taken, if we're talking a plane survey, we are dealing with vertical and horizontal lines. We're not dealing with the curvature. So we are dealing with nice straight lines, 90-degree angles, the geometry, the mathematics that we know, that we're comfortable with, that we've grown up with. When we're dealing with geodetic surveys, everything is an arc length. So that homework problem where you were given the circle, you had an arc length, you had points A and B, and we had to find the length in between them. We might need to find that arc length depending on whether or not we're doing a geodetic survey, or if we were doing a more of a tangential point and looking at just that length across and figuring that that height difference was going to be negligible. We're creating enough of a flat plane that we don't have to account for that difference there. The thing about this is what happens is when you hold up a plumb bob, let me get mine. I have toys this time. So this is a plumb bob, a little heavy, not a couple pounds probably, connected to a string. If I let go, this is going to create a hole in my desk, and if it's not my desk, it's going to be my leg, so we're not going to do that. But what this does is this weight pulls straight down towards the center of the earth. For the most part, depending on where I'm standing, that might be a different angle relative to somebody else. In plane survey, what we assume is that it will always be vertical, perpendicular to whatever surface we are working with. That's the assumption of a plumb bob. That's the assumption of plane surveying. Okay. So I once had dinner with my uncle, who was an electrical engineer, my cousin, who was a contractor. Told them I was taking a surveying class, and they both proceeded to give me a hard time about making sure that my plumb bob was calibrated. So don't let anybody pull that on you. It's like changing the air in your turn signals. Don't do it. All right, so that's the concept. We're always dealing with vertical parallel lines, not necessarily perpendicular. As a sphere, we're dealing with a flat surface, so they are perpendicular and parallel to each other. So we need to figure out, what are our dimensions? Where are we working? What do we have going on? Okay. When we are dealing with a flat plane, when we are dealing with these angles, how do we know where we are in space? Some of you have worked on the pacing lab. Okay. Taking your measurement, going out, pacing off how far, how many steps can you take, or do you take, not can, do you take in an average stride over the course of 100 feet? Figuring out that math, figuring out that step. Well, that's one way to go about it, but that is calculating out a distance. How far are we angular-wise? How many degrees of rotation do we need to go through in order to get to the next point where we need? So if I look straight out and I'm at eye level with somebody, but they're sitting down on a tall chair, if they stand up and they're really tall, then I have a different angle. So I'm going to be looking with a different line of sight. We need to figure out what all those dimensions are so we can start pinpointing our locations that we need to know about. Okay. In surveying, there are basically 5 types of measurements that we look for. Okay. Oh, this is going to be bugging me. Horizontal distance. If we were in class, I would pick one of you and say, how far am I from where you are? Okay, right now it's about 100 miles, regardless of who it is. But how far am I from where I am now over to this wall? How far am I from here to my driveway? Okay, that's what we're looking for with horizontal distances. Vertical distances. How far up do I need to go? If I'm at eye level with somebody here, they stand up and all of a sudden I'm at eye level here, there's a change in the vertical component, right? How tall is something? How tall is that tree? How deep is that gorge? We need to figure out what's the vertical. The slope. So slope distance always kind of threw me a little bit. And one thing that kind of drove it home was when you drive down the freeway and you see all that nice, neat landscaping that's going in on Highway 1, right there around Emmeline, Mission and Emmeline. So what they're putting in there, when they go out and they grade those slopes, we need to know what that distance is. We can't just say, oh, well, it's that far away. It's not a horizontal component. It's a horizontal and a vertical component. And one of the things that drove this concept home for me was the idea that we have to treat those slopes by the square foot. So if I am looking straight down at that slope from up above, maybe I've got a drone with a camera. Well, yeah, it's easy. I can measure off a quick distance and I can find out what it is between those 2 points. But if I've got a steep enough slope, then I've got a lot more surface area that I'm really dealing with, right? Over the length of the distance between those 2 overpasses. Well, when I go out and I have to cover that with a foot of mulch, fiber mulch, I need to know that value. That's going to make a big difference if we're talking dollars, right? So that's why we want to know what that slope distance is going to be. Because it's one thing if it's like this, it's another if it's going to be angled, right? So that's why we drive home the trig review. Horizontal angle. That's going to help us find some of these other components. Do we know what that horizontal angle is? Some of the problems we went through last week, right, when we were doing the trig review. One of them was there's a radio tower on top of a building. We know how far we are from the building. We can measure what those angles are to the bottom of the tower and to the top of the tower. And using our trig lesson, then we can find out what that distance is. We can find out that vertical component. What do we know? What do we need to find out? How do we get there? Okay. Lastly, the vertical angle. Okay. So how far are we out this way? Horizontal angle, vertical angle. No, I screwed that up. All right. So one thing to watch out for, one thing to look at is stationing. So when you're reading a set of plans, and this is where, Kenny, this comes to your point, roadways, dams, when we might need to use curvature in order to ensure alignment, ensure elevations and drainage. So what we're looking at here is a sample of a screenshot, is a part of a plan set from a Caltrans contract right out here, actually by my neighborhood. Highway 99 runs north and south throughout the state of California, covers the east side of the valley. I-5 kind of takes up the middle and the west side. But both of those pretty much run the length of the state vertically, north-south. So we need to identify where are we on this highway? What's our starting point and what's our stopping point? So we need to identify this by stationing. And the way stations are referred to are by that initial number, typically going down the center line of whatever alignment we're talking about. But we start with that initial number. We are looking at the number 435. What that is telling us, stationing is usually read with a plus sign associated with it. So 435 plus 00 is actually the station at that hash mark, okay? The plus 00. That tends to throw people, that tends to get a little bit a little bit confusing sometimes. So we don't have enough room to write on there the 00, which is the extra, which is the hundredths, right? So we are looking at 43,500 feet. Well, how many feet are in a mile? Anybody remember that? Or can Google it quickly? Awesome, thank you, John. 5,280 feet. Okay, so if we're talking 435,000 feet, or no, 43,000 feet, we're talking many, many miles. What, 8 miles from the beginning of where we started measuring. So the absolute dead on 0, 0, 0 plus 0, 0 is the beginning of that measurement system. So when we get to things like 435 or over here 440, then what we're talking about is we're further and further away from that origin point. But we still have those points of reference, not only back to the origin, but also going forward and relative to each other. Okay, stationing is typically brought out in hundreds of feet. Okay, one station equals 100 feet. It can depend on the scale that you're looking at as well. There's another screenshot that I could grab from the same exact set of plans where they go every 10 stations because they're zoomed out so far that you would lose that detail if we looked at every 100 feet. But you can always take a plan set that has been stationed and you know that this distance between those 2 points, between this 8 and this 9, is 100 feet. I can find that scale every time. So what we look at when we're dealing with stationing, it tells us a lot about what we're doing and where we're doing it, okay? What this is telling me on this particular set of plans is that based on this alignment, this SR99 right here, at this station, that's where we start removing our fence. Now, if we're getting paid by the lineal foot to remove so much fence, we don't want to start before that. We want to know exactly where we're starting and exactly where we're stopping because that's all we're getting paid for. Anything extra, that's coming out of our pocket. So you're getting a lot of this from the contractor's perspective, right? So as engineers going forward, be very specific. If you want it going back to a certain point, make sure you measure that out. Make sure we've located exactly where that is. So the way to read that stationing is that we are going to start removing the fence at 437 plus 37 and 2600ths, or 37.26. Okay, what that's telling us is that from our 0, 0 coordinate system, our 0 point, we are going to be going 43,737 feet, 0.26. So about 4 inches, 3 inches. Okay. From that point, that's where we're going to start. So we always like to take our known points of reference, and we're going to come back to that a lot. What are our known points of reference? What do we know? Where do we have official data that tells us exactly where we are in time and space? That's the important information that we need. That's what we need to get across. Okay. So let's do some stationing examples. Okay, I've got about 4 slides, different styles, different methods. Let's look at what we get from those stations. So if I tell you, make sure I got all this. All right. All right. So we can use the chat. You guys can chime in. Feel free. So if I say that I'm at station 1 plus 0, 0, how far am I from the beginning, these are all from our 0-point reference. Okay, seeing a couple chats. Nice, that's exactly it. We're 100 feet from our starting point. What about the next one? Station 12 plus 00. Great. Nice. Okay, seeing a lot of 1200s. Correct. So we weren't very creative in our numbering system here. So what do you think the next one is? We're at station 123. Okay. Those 00s, it's just that 100th point. It's the ones and the 10s. Okay. So you can guess where we're going with this one. This one we're starting to add to the right of the plus sign. So what would the next one be? Enio, excellent. Good job. That's it. 12,345. And just like we saw with the fence, now we've got decimal points. What would we have there? Easy peasy. Yes. Okay. Does anybody have any questions so far before we move on? Too easy? All right. Little harder now. So based on that first one, 35, station 35 plus 87.5. Okay. That's it. 3,587 feet and 1/2, 6 inches. Okay. If we say we're at station plus 5.5, we know we're 5.5 feet beyond that benchmark point, right? That's what gives us that definition. Really easy to say 5.5 feet, but once we get down here towards the bottom, if we're at station 1335 plus 09, it's just a frame of reference. It's a way of communicating. So speaking of which, how far are we from our 00 point? Okay, you guys were on a roll. There we go. Thank you. Yeah, that's it. 133,509. Saw 309. I think that's just a typo. Okay. So what about the next one? Why do I have 2 of these? That's correct. 968 feet. That's right. Oh, sorry. What's this last one going to be? All right, throw in some commas. Because that's what throws us when we start looking at these, is I see that comma in there, but then I've got to move it in order to make the number make sense, right? Yeah, 82,562. Wait, 82,562,205 feet from my starting point. Way the heck down the road. If I have stations like that, and I am still incorporating that 00 benchmark, that beginning point, and I have that kind of a distance that I'm dealing with, I definitely want to take into account the curvature of the Earth. I really do need, that is going to make a difference in terms of my elevations, my ultimate elevations. Yes, 82,562,205 feet. All right, duplicated the slide, sorry. All right, so a little more fun. If I tell you I'm at 400 feet, what would my station be? Got to be able to go both ways. Correct. Othello, don't forget that plus 0, 0. Okay, that plus 0, 0 is what tells us we are dealing with stationing. Got it. Typo. God. I'm getting trigger happy here. All right, so perfect. 4 plus 32. Absolutely. All right, how about the next one? Whoa, that's a fun one. I think I have a typo there. Okay. Correct. That was supposed to be a decimal point, not a comma at the 25. So let's try the last, second to the last one. 798,000 feet. That's it. So it's much easier to say, hey, I'll meet you out at station 7980. Right? You know where you are, you just get to drop all those zeros. Last one. That's it, plus 25. All right. So that is the nomenclature for our horizontal definitions. If we're starting to talk about large scale, we're going to start talking about stationing. We use that a lot in on the construction side, especially when you start getting these large projects that go miles and miles. Okay. So the next component that we have is going to be our vertical control. So there's a little bit of a history behind the vertical control side of things. Okay. So we say that an elevation is the vertical distance between 2 points. However, there is also what we need to refer to as a datum, and that is the vertical distance from a known fixed point. Globally, we use what's called mean sea level, right? What's the average, basically average, sea level, and that's our 0, 0 point. Anything below the ocean is a negative number. Anything above the sea level is going to be a positive number. So a datum that's everybody's fixed reference point. It's so we all begin with the same information. Okay. So there's a question. Would people say station 4 plus 32? Yes, absolutely they would. Absolutely. Hey, where does that new curb ramp go in? Where are we putting that new piece of curb and gutter? Well, that's going to be at 4 plus 32. So you could definitely hear that on a job site, especially when you start getting specifics. Like, so if we're looking at this again, you're going to start getting a lot more specific. Oops. Sorry. Okay. You're going to be pretty specific. I'm going to tell my fencing subcontractor who's going to go out and remove that fence for me. Yeah, you're going to start at 437 plus 37. So they can start out on their plans, and if they open up any set of plans, they can look and see, okay, well, there's station 435, and you can start getting your bearings on the job. Okay, well, that off ramp that we're talking about, that's at station 445. And whether you're going north or south, your starting point of reference is always fixed. Okay. I believe on this one, based on the way the numbers are going and from what I remember about where the north arrow was, we are starting actually from the south and measuring north from the county line. So that appears to be what we're looking at here. So we're about 8 miles north of the county line at this location. Okay. So yeah, absolutely. That's how they'd probably refer to it out on the job site. Okay. Where's our cut? Where's our fill? Where does our bridge begin? Well, it's going to start at 437 plus 37 or 4 plus 32. Okay. So let me get ahead here. We'll come back. All right. So vertical controls. We all have to have the same point of reference, right? In terms of that vertical control. We deal with such large distances horizontally, miles, kilometers, hundreds of thousands of feet, right? But we really don't have that much variance when we talk vertical distances. I mean, if we look at, let's say, Everest, right? The height of that, 29,000 feet. We were looking at stationing of 43,000 feet, all within one county, let alone a nearly unscalable mountain, right? So we tend to be a little bit more correct when we start talking about vertical differences. Okay, what's the distance vertically? We're not going to use something like stationing. Stationing cuts down the number of significant digits. Vertical distance, we need to get a little more precise with that end of it. So datum, that's our fixed point. That's our shared point of reference. Mean sea level, we used to see the abbreviation MSL, right? It's the vertical distance from mean sea level to our point that we're looking at. The government established the National Geodetic Survey, called this mean sea level the National Geodetic Vertical Datum. How's that for fun? NAVD, the North American Vertical Datum. And they have put together a chart and a catalog of where that point is. Where is mean sea level? Not to bring politics into it, but they started out doing this in 1929. In 1988, the oceans had risen by about 2.5 feet. That means our mean sea level changed. So our whole datum then moved. So they've come out with new versions periodically. And this is showing, this verticon, this is showing the difference between the elevations in 1929 and the elevations in 1988. Okay. So vertical distance, we take those known elevations, and that's our beginning. There's conversions. The interesting thing that I found out while preparing for this was Google Earth doesn't use this system. They do use a world geodetic system. So they're going to be more on that big scale, that large geodetic survey kind of concept, right? What that does is that is based on the Earth's center of mass. So that image that we looked at showed kind of the Earth had like a little Igor hump kind of going on, right? So that's going to shift the center of mass depending on where everything is, right? Where are our points? Where's our heaviest locations? That can vary significantly from the vertical datum that we use in plane survey. That can be almost 5 to 10 feet different. Okay, so we see that we've got a big swing between the vertical datum just across the United States from 29 to 88. But then when you start talking about geodetic data based on the spherical concept and the vertical datum based on plane survey, there can be big swings in terms of what the elevations are. Okay. So if we were sitting in a classroom, pretty typically right there on campus, there is a survey marker. There is an elevation point that's been sited in and it's been located, I believe, right off the end of one of the buildings. So if that were the case, we would go out, we would go look at it, ooh and ah over it. Based on where Cabrillo is, where the campus is and where the engineering building would be versus our mean sea level, where's the ocean? Anybody know what the elevation is of Cabrillo up on that hill? Nope. Keep going. We got an 88. Threw me too. Anybody else? I worry about saying this because I don't want to. Viridiana, that is absolutely correct. It's actually about 230 is the elevation at Cabrillo. Okay. So if we look up here on the hill versus down here at the sea level, we're talking about 230 feet difference in elevation. Okay. So when you look at topographical maps, if we look at what those are telling us, and those are the more fine, well-defined elevation differences between points in a smaller area. But those beginning points, those beginning elevations tell us kind of where we're starting. So if we were going to go out and work on a parking lot just on the east side of the buildings there and build out something along those lines, we would be looking at elevations of plus or minus 230 feet from our North American geodetic datum, okay, vertical datum. So how do we know that that's at 230 feet? The benchmark that we would look at, that we would go out and we would ooh and ah over, resume slideshow, okay, fine. Okay, there are various types of benchmarks that we use throughout all of the various industries that need to know this information, that use these reference points, okay? So that first picture showing the brick, the benchmark is because, for example, where I am, as far inland as I am, getting a survey out to the ocean to figure out where mean sea level is and then work my way back to Sacramento, it's going to be quite intensive. That's going to take a lot more effort. We could get it done if we were talking about going through house, but even still, with those cliffs, that's going to be a little bit of a challenge. Going to have a harder time getting that done. Okay, still possible. So we need those benchmarks to kind of leapfrog out into the big wide world and figure out where we are and have our own reference points relative to that datum. Okay, so that symbol in the brick, that is actually, that's one of the original benchmarks. Has anybody ever seen that symbol before? Wandering around old village squares or anything? Yay, nay? All right. Well, what that is, the name benchmark actually came from old time surveyors creating a bench, creating a flat level spot in a fixed point so that they could always go back and had something to put their rods on. They had something to rest on of a known location. And so that's what those symbols became to be known as. Those were the benchmarks. Looks like a surveyor's tripod with a nice level piece, and that was where they would come back to for their points of reference. So I doubt you'll see very many going around Santa Cruz or the communities around there. More than likely, if you go further east, much further east, or probably even Europe, you might see something along those lines. Okay. The next the next image that we've got, that is an official benchmark. That is a permanent benchmark. It gives you the elevation. The little plus sign in the middle tells you exactly where that was measured. Okay. Those have to be treated with care, with caution. You've got to watch out for them if you're out there working. Big, heavy construction equipment can make those disappear really quickly, and people get really mad. So where is it located? Who is in charge of it? Who owns it? This was from the USGS, the Geological Survey. It's a known benchmark. It's a fixed point in time, in space. Okay. This little nail is actually a temporary survey marker. So we might start with a USGS benchmark, and the surveyor will go out and, based on that information, locate a point within our site where we would be working, where we want to design our project, and we would put a temporary mark there. And that's what that pin would be. They're also called PK nails. And you see here in the asphalt, in this last picture, this is actually in Dublin, Ireland, and that's a temporary marker as well. So they're using that as their benchmark for that project. So that's where the liability insurance, the errors and omissions insurance comes from for engineers and surveyors. Because if you're off a little bit and somebody has been using that as their frame of reference and you certified it, all costs are on you. So that can get kind of expensive. Okay. All right. I'm going to skip ahead a little bit here, resume our slideshow. You guys ready for a break? Want 5 or 10 minutes? It's 7:25 now. Okay, I'm seeing sure 10 minutes. All right, 7:35. Nope. Sorry, it is 7:30 right now. 7:40, we'll reconvene. All right, we are back live. Everybody back? All right, couple thumbs ups, thumbs up, thumb ups. Okay. Thank you all very much for coming back. Actually, I'm really surprised you're all here this week. Oops. All right, so we're going to skip over this particular slide. Basically kind of what we talked about already. We're looking at the actual surface of the slope. So those weren't supposed to come in till later. First up, we've got a slope. We've got space between two different points, right? Different elevations. We're going to treat this as though it's going to be a right angle. And if we know that angle, we can use the tangent property from trig to find those values, right? We can find our horizontal, we can find our vertical. Pythagorean theorem allows us to find our hypotenuse from there. The other option we have is to look at a rise over run. How far up do we go for a given distance? We usually convert that into a percent so that we say it's whatever our rise is for every 100 feet. Okay, so it gives us that sort of analysis. So we'd have our rise over our run. Lastly, we would look at horizontal to vertical, and that's going to give us more of a ratio, right? Our slope is going to be a 2-to-1 slope. For every 2 feet we go horizontal, we'll go 1 foot vertical. Our vertical, our horizontal components. It's just a matter of breaking it down into each of those 3 options. So what do you think we would do? How do we come up with those slope measurements? Where do we use the different options? So for example, where would I use an angle from the horizontal? Okay, I'll give you this one. But someone needs to talk on the next one. All right, we would look at something called the angle of repose. So in geology and in geotechnical engineering, if you take a pile of materials, a pile of rock, for example, a pile of sand, and the reason I'm using sand is because that's one of the angles that I always remember. If you were to take a bucket full of sand, probably even beach sand, turn it over and dump it down onto the ground, and it forms a pile. The angle, the natural angle that that material will hold is 35 degrees off the horizontal, okay? Every material has its own angle of repose. So if you look at a slope and you know that it's mostly sandy materials, you know that about a 35-degree angle or less will be relatively stable. Rule of thumb, no hard and fast guarantees, especially when it comes to earthwork, okay? So the next one we talked about was rise over run, where we get a percentage. Imagine you're out driving around. Where would you think, where have you seen percentages before?
Right. Percent grades, I think someone else said it in the chat as well.
Oh, my chat's hidden. Damn. Yes, absolutely. It's percent grades. Why do we need to advertise that? Am I sharing my screen?
Not right now, no.
Oh, this is so much fun. All right, there we go.
Now you are.
Get my chat back. All right. So, yes, percent grades. So now that I've fixed my end, why would we want to know the percent grade?
Probably to know if it's stable or if it needs to be needs some reinforcement. If it's
True.
like close to the angle of repose or below it.
But when we're looking at percent grades the street signs that you see, the road signs. So this is actually, I can never pronounce it. This is the Grapevine. I-5 in between basically Bakersfield and Los Angeles. Some pretty steep hills there. What's the symbol that they're showing?
They're showing a vehicle, right? That's what I was considering, because heavier vehicles might have a harder time.
Absolutely, yes. Not only going up a hill, you might see a sign that says steep grade ahead. It tells the truck drivers, hey, you know, if you've got a big load, you guys have probably all seen it on 17, everybody's in the fast lane because you've got one truck struggling to climb that hill, right? It's trying to get that mass up that steep slope. So the percent grade tells the truck drivers not only I better get ready to get up that hill, but what kind of braking resistance, what kind of force am I going to need to slow my truck or stop it if necessary? What happens if my brakes don't work? They need to know what they're prepared for. What kind of ground am I dealing with, right? Is it super steep? Is it steep? Is it not very steep? Okay. So anybody know where, and I'm thinking a very specific one here, and this is, again, I'm coming from the construction side. So when we talk about horizontal to vertical comparisons, if we're talking about a slope, a 2-to-1 slope, a 1.5-to-1 slope, so knowing the angle of repose is based on the soil type. Then we need to look at the soil type that we would be digging in order to process our, in order to lay pipe. So this is a pretty typical image that you'll see. What type of soil am I dealing with? Is it good soil that's going to stand up and it's going to be safe for my people to enter, right? I might have to dig this little box and then slope it back at a 1-to-1 slope. Okay. I might not be able to do that little bench. If it's soil, I'd have to do a 1-to-1 slope. If it's really bad soil, if it's sand, if it's, we call it sugar sand. You start digging and it's like dry beach sand. It just starts running into, it's like when you pour sugar out. It just crumbles, falls apart, right? There's no cohesion to it. There's no stickiness. So if it's really bad soil, we would say that that's a 3-to-1 slope. Okay. The horizontal component, we have to go over 3 feet for every 1 foot we go down. So those are areas where we would use those different kinds of slope measurements. The angle of repose is an example based on the type of geologic material. The percent grade, we look at that for roadways so that we can alert people to dangers, potential dangers. And then slope stability. We're looking at trenching operations. Can I trench vertically? Can I lay it back? How far back do I have to lay that slope in order to make it safe for my people to be in that trench and doing the work that they need to get done? Okay. Fun little bit of trivia here. Not only do we, and I say we in the construction sense, if we are creating a trench for storm drain, for sewer, any of the gravity lines, okay, where we are not required. We are trying to get a flow so that we don't have to pressurize the pipe and push material through. We just let gravity do its job. So we will talk about having a trench that is a 1-to-1 trench or a 2-to-1 trench, but then perpendicular to this, the direction the pipe is going to go, that will have a slope that's going to be a percentage. So you never know when you're going to have to deal with both. You could end up with both of those on the job. Okay. Slope equivalence. So I've got my horizontal. What is my ratio? What is my percentage? What is my angle? What's the conversion between them all? That's what this chart is going to show us. Okay. Angles. So during the quiz, I got a few questions about, how do we identify a unit of measure? Putting that little degree symbol on things is kind of tough. You got to know where to go to find it, and most programs don't have it. So from here on out, moving forward, we're not going to use radians. We're not going to use decimal points in our angular measurements. We want to report it in degrees, minutes, and seconds. Okay. 84 degrees, 34 minutes, 2 seconds. Easy conversion, minutes and seconds, just like the hour hand on the clock. 60 minutes for a degree, 60 seconds is 1 minute. So conversions are pretty simple. Okay. Now, I copied this over from the last presentation. On your calculators, I have not seen other scientific calculators in a long time. I mean, I don't even know where I put it. There are buttons for DMS, degrees, minutes, and seconds, or you'll see the icons, the degree symbol, the minute symbol, and the second symbol. Does anybody have an HP scientific calculator? Old school. Because there is a 3-page document on how to convert and display in degrees, minutes, and seconds. Does anybody have a use for that? I can post it to Canvas if anybody wants. I can also delete it off my computer and never look at it again. Just let me know, okay? So any questions on how we're going to report angles from here on out? All right, take that as a good thing. Direct and indirect measurements. Any ideas on what those are, how they differ? Anybody? Oh, here we go. So Kenny posted, indirect is when you cannot see the finish from the start. Somewhat. Yes, along those lines is where we're headed with that. Kind of where we're going with this one in particular, though, is we're going to say that a direct measurement is something we can physically measure right then and there. So, for example, I don't know if you guys have seen these before. These are measuring devices that are really great for creating blood blisters on your fingers, in case you ever need to. Marcine, thank you. Marcine posted in the chat box that if you have a TI-30X calculator, she posted where the DMS button is, so you can find it. If I can use this to determine a measurement, that is a physical measurement. How wide is my iPad? I can measure that. So that's what we're looking at for when we refer to direct measurements, something we can physically measure. Indirect measurements are going to be a calculated value. So I can't actually, well, I could, but it's kind of a pain in the butt to go out and measure an angle, right? However, I can measure some sides, create a right angle, a right triangle, and I can calculate what the value of that angle is going to be. And that would be considered an indirect measurement. So unmute yourselves. You guys get to participate here. Give me some examples of physical measurements, of direct measurements.
Like a bed?
What's that?
Like a bed?
Yeah. What part of it? What would you do?
The length and width to find out what size it is, or the height to find out maybe for a bed frame?
Okay. So you said length and width to find out what size it is. So that kind of comes into a little bit of a gray area. And I wish I didn't bring this up because I don't actually have the answer to this. Would the area then be a calculated value or a physical measurement?
I think it would just be using the lengths and widths to find out if it's like a queen or a king, you know, to figure out like what sheets you need, rather than
Right.
finding the area. Or would that still fall under the same?
Same thing.
Okay.
Same thing. Well, so no, okay, I get your point. I get your point. Mason, yes, a door opening would be a good example. Measurements taken there. Anything that I can measure. I also have nice and handy a sewing tape. Okay, if I need to measure anything, a circumference of something, I can do that. Back to the length and width. If you had a chart that said this length, this width is a queen or a king size bed, that would be a physical measurement. What I was wondering was if I calculated the area of it, if my chart was based on areas. A queen bed is so many square feet. A king bed is so many square feet. That's what I was overthinking. Does that make sense?
Yeah, that makes sense.
Mudding the waters. Okay.
Yeah. No, I got you.
So good examples of physical measurements, right? Length, width, height. Okay. I mentioned circumference. How big around is my cup? I don't know why I'd need to know that. Just curiosity. You know, maybe I get a wild hair and decide that my dog needs a new collar. I've got to measure his neck. Those are physical measurements. Those are direct measurements. So what about examples of a calculated value? Kind of threw one out there.
Square footage of a house?
Yes. Yes, absolutely. Okay. How big is the house?
Parcel also.
What's that?
Size of a parcel.
Absolutely. If we have an irregularly shaped parcel, how much land do we have? How much land are we talking about? We'd have to calculate that value. So this is going to lead us into some trickier concept here. What kind of errors do we get with physical measurements? What can go wrong besides everything? Okay. What if I misread that tape? What if I say it's 10.5 inches, only I missed a little spot and it's actually 10 3/4? So we can have errors in our physical measurements. Okay. What about our calculated values? Okay, yes, yes. Measuring device not calibrated, human error. God, that's a big one. That's all over the place, right? Everywhere we go, everything we do. The numbers. Hey, Jesus, you talking about like transposing numbers or typos? Yeah. So the calculated value, we run it on a calculator, then we write it down. We don't write down the right number. You miss a decimal point. It happens. Okay. So excellent feedback. Thank you, everybody. Direct and indirect measurements. Direct, I can physically measure it. Indirect, I have to come at it a different way. I can calculate it. So that's going to be the difference when we're talking about different types of measurements. All right. Accuracy and precision. So this is going to be part of the reading that's coming up that's going to be assigned. So let's talk about accuracy and precision in measurements. Anybody ever take a gun class? Shoot targets? Okay. So Mason, if I can pick on you for the point of this presentation. Louise, let me say it is. I loved it. What would we say in terms of accuracy and precision about target A? Brandon, you said yes too, so either one of you can chime in. Anybody can chime in.
It's precise, but it's not accurate. The grouping is good.
Okay. Yes, we would absolutely say low accuracy. We didn't hit where we wanted to, which is going to be the bullseye, but we're very precise in terms of consistently hitting where we hit. Okay. Mason, you're absolutely right. Human error, sights are off, or you're just a really terrible shot, which is usually me. I'm more like D over here. Okay. Yes, low accuracy, high precision. What would we say about B? Okay. High precision, high accuracy. Correct. Okay. That's what everybody's going for. That's what we all want when we go out shooting. Okay. What about C?
Accurate, but not precise.
Very correct. Yes. High accuracy, low precision. Okay. Still not bad. Okay. And last one.
It's not accurate or precise.
Absolutely. Low accuracy, low precision. So, which one do you want to be?
I'm gonna be B.
Both. We want that accuracy. We want to hit exactly where we are intending. And that precision, we want to hit same place every time. Okay. Accuracy means we are on target. We're close to the right answer. Precision means we do it over and over and over again. We consistently get that same answer. So I liked this example. The bullseyes really drove it home for me and helped me understand what we were looking at. Yeah, we want to be accurate in what we do. We want to be precise. We want to be able to repeat it every time. Okay. So if I were to go out, if we were to measure, what should we measure? If I were to go out and I were going to measure across some parking stalls, let's say 4 parking stalls. Okay. I don't know how wide they are. I have a ballpark, I have a guess, but I go out and I measure those 4 stalls. And I come up with 100 feet, 101 feet, and 98 feet. Hint, the width of a parking stall is about 12 feet. Am I accurate or am I precise? Yes, I am precisely incorrect. I am consistently wrong. Okay.
So I have a quick question about that. Does that make it easier to solve problems then that arise in calculations?
Only if you have a ballpark of where you should be. If you don't know what exactly you're aiming at, then it's hard to be accurate.
Right. That makes sense. Yeah.
Yeah.
So, yeah, because I'm just trying to understand if you make a mistake somewhere, then you can go back and it's more readily fixed. If it's more precise and you can base it off of somewhere you're supposed to be.
But the hard part is if I go out and measure it 3 different times and I'm close, I'm very close on each one of those 3. If I'm consistently off, then what I'm getting is a false sense of, hey, I must be on the right path because all 3 of my measurements were very close together.
Right. Yeah.
Doesn't mean they were right. It's
Which
hard.
makes
It's
sense.
hard to tell without that target there. I'd say, hell, this A. Can you guys see my mouse?
Yeah.
Okay.
I can see it.
I would say A. Hell, if I didn't have that target there, A is wonderful. Just as good as B. But it's not accurate. So we have to find the balance between the 2. We still have to get the right number, not just the same number. And finding that's the challenge. That can be a challenge. Absolutely. So we'll talk about ways of trying to minimize that by looking at where should we be, right? Should we be in the ballpark? What is our range? Am I within 100 feet? Am I close? So any other questions on accuracy and precision? All right. So, Othello, to your point, the next thing we're going to talk about is actually methods of measurement. Okay. And the first one is going to be pacing. We're going to talk about pacing. That's not supposed to be there. A pattern of your steps. How long is your stride? How many steps do you take within a specified distance? The catch here is you are required to have a known distance. If I'm out on a football field, I have known markings for distance. If I'm on a running track, same thing. If I have one of these things, I can measure it out, right? I can find out how far it is. I'll leave that there for now. I have goodies. All right. So what we are looking at is from the tip of your toes of your left foot, as you take a step, to the tip of the toes of your right foot, that is a pace. That is one step, okay? From toe to toe, or from heel to heel, as long as you are consistent in that measurement. We're gonna say from toe to toe is going to be your pace. How many of those do you take to cross 100 feet? Okay, so then what we're going to look at is an example here. We have Roland, and he goes out and he measures it 6 times, right? He walks that 100 feet 6 different times. He comes up with those values: 38 steps, 39 paces, 41, 38, 37, and 42. What is his average pace length? What is his stride length? Okay. How do we find that out? Well, first we need to find the average number of paces to cover that 100-foot distance. So this is where we want that precision. We would like to see it a little more precise. We don't want to see a 50, a 55 in there, a 20, 22, with all those other numbers being so tightly grouped up in those upper 30s. So here we are looking for that precision. The accuracy comes because we are repeating the process and we have control over that process. We are careful to make sure that our stride stays the same, that we follow the same rhythm of one foot in front of the other, okay? We try and keep that consistent. No skipping, no running, no hopscotch, a nice steady walk, okay? That's how we measure our pace. So he's got those counts. The average length is going to be our total distance, which is going to be a measurement of length. And then the average number of steps. How many feet per step are we calculating? So we need to calculate the average of Roland's various steps. 38, 39, 41, 38, 37, 42, and he did it 6 times. So let me see if I remember how to use my old calculator here. I got 38, 39, 41, 38, 37, 42. Oops, no, I don't apparently. All right, anybody else get 235 total paces?
No.
Yes.
Okay. I got 39 and 1/6. Somehow I've got my calculator displaying fractions. Okay. So what I would want to do is take 100. Where's my switch my X and Y? There we go. And then divide that. I get, all right, what did you, anybody else do it? What did you guys get?
Yeah, so I got around 2.55 feet. So I'm going to try and change that to fractions.
No, don't change it to fractions. We want
Yeah.
decimals.
Yeah, so.
Whatever 26 divided by 47 is, which is apparently 55. Yes, so I got about roughly 2.5 feet.
Right.
Roughly. So pacing done consistently is actually very accurate. You can be to within 1/50th or 1/200th of the actual measurement when you use pacing. Okay. The thing I always found to be difficult was trying to pace in uneven terrain. It's one thing if you're out on a sidewalk, if you're on a street, a football field, it's nice and flat, nice and level. But if you've got some little hills and some draws, it's a little harder to get that consistent, to get that accuracy of repeating your steps. So one thing to watch out for, maybe it's something that we need to correct for later on if we use pacing. Oh, all right. Any questions on that? You're going to need that formula if you haven't already done the lab yet. Okay. Because I'm pretty sure that that's the lab, is you're going to figure out your pacing. Okay. All right. More distance measuring. We're going to see if my animations work on my slideshow here. My pacing. All right. The length of your stride. How many strides over the course of that distance multiplied by the length of your pace that you've calculated from an average. Okay. Sorry about that. All right. So pacing is one way to calculate, to gather a distance measure. Oops, come on. Odometer readings. Odometers are not just for your car, right? We have, I should have brought it in, but there are wheeled devices. Looks like a little cane and a wheel on a stick, and you go out and you walk it, and this pointing to it really helps, doesn't it? Oh my God. These little meters click off as the wheel rolls and clicks. Okay, so it's a known circumference, so each revolution is so many feet. It goes so far, and you can get a lot of information out of something like that. Okay. We also have special devices that I've seen in our in the pickups of some of our foremen. They can turn it on and they can drive slowly and easily, and instead of using the odometer on the vehicle, which is going to go in tenths of a mile, they can actually measure in feet or in meters, so they can get more accurate measurements in terms of finer detail, right? So odometer readings, that's one way to go about it. Okay. Chaining. Chaining is old school. As you can tell, this is tied with twine. Actually, that looks like straw. Okay. Let me get to my, oops. My notes are in the wrong place. Oh. All right. So chaining. You guys already saw in some of the homework, some of the reading? I can't remember anymore. We talked about Gunter's chains, right? We didn't talk about it, but that was question number 6. Awesome. Okay. Thank you. Gunter's chains from the late 1500s, and they're a fixed length, right? It's 100 wire links, and this is a really, you know, who pulled this one out of their hat? 7.92 inches long, not 8, not 7.5, 7.92. It's because that ends up being equivalent to 66 feet. Okay. So that's where we came up with the US measurement of acres, was based on a chain. Okay, 660 feet by 660 feet gives us 1 acre. basically this is an obsolete method. Nobody really uses this anymore. If you see one, it's cool, it's old school, but you're probably not going to be asked to do anything with chaining. So next up, chaining, taping. Steel tapes. They're heavy. You don't want to carry this around in 110-degree heat all day. They're unwieldy, they're cumbersome. I can't even find the end of this one. This one's over here, okay? So, and it's not painted on, it's indented in, it's embossed. So it doesn't lose its markings, okay? This is what we usually use. So this one's still around, right? You'll see nylon ones, fiberglass ones, more modern looking ones, but these steel tapes still work. They still do the job. Yeah, this one's probably about 3 pounds. I don't know. I have to pick up my dog for comparison, but she's chunky. All right. On a reel, they're much easier to use. Back when I was taking the surveying class, they weren't on these reels. You had to wind them up manually, and if you didn't have them going in just the right direction, one would flip around. Anybody remember the old phone cords that would get all twisted around? That's what these would do. Question, and this is just out of my curiosity. So I showed you the rodeo thing before. Anybody ever team roped or swung a lariat? No? Yes? Okay. Because when something has this kind of rigidity, I'm probably using the wrong term, it's been a long time since I took materials. Anytime it has this kind of life to itself, you have to work with it a lot more carefully. And for ranch rodeos, for team roping, things like that, the ropes themselves are very similar to these steel tapes. They have kind of a life of their own. They've got a body to them. You can't just bend them and manipulate them. They're going to do what they're going to do. So you have to learn to work with them instead of against them. So anyway, so these are tapes. They can break very easily, right? The steel, anybody taken materials yet? Wear and tear, fatigue. So these can end up breaking. Let's see. The next one here is, swift measurements, okay? This was used up until pretty recently. There was a 2mm horizontal bar with sighting marks. It was mounted on a tripod, okay? And you turn it to basically perpendicular to the line you were trying to measure. It figures the angles, right? It calculates on the angles. Again, this is not something that gets used very often anymore, kind of old school. So we used a stadia. Chapter 3 discusses these kinds of components and configurations. So it will be part of the reading going through that. Since we have this fixed distance, which is going to be this bar here, we're able to calculate those areas or those distances. Okay. Again, I stole this from the previous instructor. EDM, bad joke, it's coming, bear with me. No, not that. basically it's electronic measurements. Okay, total station. That's more what you're going to use. You're going to end up using a lot of these. Total stations can do not only distance, but they can calculate angles as well. They have internal calculators. You can reduce the size of a surveying party. If you're wandering around trying to maneuver these tapes and these chains and place pins, you're going to need quite a few people to do this. We've got a video coming up that I'm going to show that goes over taping, and you'll see how many people are out there working on this project. A total station, a couple people. That's really all you need. Okay. This is incredibly precise. 1 in 20,000, 1 in 300,000 of a micron. Okay. Horizontal, vertical, and angles. Oops. Keep. All right. So, you guys ready for a video? We're going to see how this works. See if I can get this to happen. All right. Are we seeing the video?
No.
I don't.
Got it now?
I can see it now. Yeah,
Okay.
it's working.
All right. Now, stick with me. We're going to have to try and figure out the audio on this. See if it's too loud, not loud enough.
To another UCLA surveying instructional video. Today, we will be measuring horizontal distances with taping. The process is easy to learn, but first we need a few pieces of equipment, such as steel tape and a tape clamp handle, 2 plumb bobs, a force gauge, pins to mark points, a hand level, and of course, your surveyors. Now that we have everything we need, begin from your starting point and unwind the steel tape. Once the end of the tape reaches the end point, pull the tape using the tape clamp handle to the nearest hole foot at the starting point, while making sure that the pin at the other end is in the red area. Now, with the force gauge, make sure you are pulling with 10 to 15 pounds of tension. At both ends, use the plumb bob to double check that the tape is directly over the point. Then use the hand level to check that the tape is level. Since the steel tape will droop over long distances, have one person in the middle hold the tape. Now, to record the actual measurement, note down the number at the starting point. This will be the measurement to the whole foot. At the end point, the pin should be in the red area. These numbers tell you how many inches and fractions of an inch you need to add to the whole foot. Record the complete measurement. If the distance you're measuring is longer than the steel tape, in this case 100 feet, you will have to divide the distance into 100-foot segments in a process called break chaining. Follow the same procedure as before with temporary endpoints and starting points at every 100 feet. Record the final distance. If the area you're measuring has a considerable slope, position one end of the steel tape at the highest point and use a hand level and plumb bob at the other end to ensure that the tape is level. Thanks for watching. To learn more about taping and other surveying techniques, come to UCLA Surveying Workdays.
Wasn't that fun?
Yeah, it was kind of interesting. I didn't really think that there would be that many tools to be used with just steel tape.
Yeah. Yeah, you would think, oh no, I'm just going to go out and I'm going to measure something. I got a measuring device. That's all I need. We get way more into it, and that's why it takes a whole semester to cover this stuff, right? All right. So they talk about using a steel tape. That wasn't steel that they were using. I mean, you can tell by the rigidity of this thing what we're talking about, the difference that we're looking at, right? So, like I said, fiberglass, nylon, a lot of different composite materials. The steel, truly steel tapes are falling by the wayside. They're harder to come by, and they're heavy. You know, if you've ever held one of the other ones, you're like, oh, yeah, there's a big difference between these. And lugging around 2-3 pounds, plus all the other paraphernalia, a heavy plumb bob. Then you've got all your chains, so you've got to carry those with you. Now you know why these guys had big tool belts, right? You need your level, you need your, there it is. This little device holds on to the end of the chain so that you're not pinching it. This will pinch it for you, okay? That's a lot of crap to juggle. Then you got to start marking things down. You have to have your notebook, you have to have your pencil, you got to have your calculator. Yeah, there's a reason we developed better tools for this stuff. However, okay, whew, that was a lot. So, talking about steel tapes, problems with them. What do you think, what kind of issues do you think we would have with steel tapes? What kind of things do we need to keep in mind when we're measuring steel?
You need to be able to take it slowly and be patient. That way the tape's not moving around.
Yeah, absolutely. Okay. So you saw as they were going out across the field, you know, you can vary a little bit as you're going. You might go slightly to the left the first time, then you set your pin if you're brake chaining, and then you might come back and you might be a little bit off to the right. You might not be in a perfectly straight line. That's another problem that you might run into, the accuracy you've got there. So what did they talk about in the video? The keys to taping. Okay. You saw how many people they had on their team. Okay. You need to keep it level, absolutely. Okay. Teamwork, definitely. Taking good notes. One of the big errors that we talked about earlier was how we might misinterpret the numbers. We might misread the tape. We might write down the wrong number. So we've got to watch out for things like that. Keeping the tape level. They had somebody in the middle kind of holding it so that it didn't sag, and they were just at 42 feet. Now, if you had this big heavy tape stretched over 100 feet, you're going to get a lot more sag to it. You're going to get a lot more droop. Also, if you're standing there, let's see if I can do this with the camera. All right, so you're standing here, you're looking down. I'm not overly tall, I'm only 5'6", but if I'm looking down, that's still a long way for my eyesight to try and identify that pin down in the ground. Anybody much taller than that is going to be even further away from that pin. How do I know if I am looking at, let's see, can you see these teeny tiny little numbers? Okay, if I'm looking at that up here and I'm trying to line it up, that's going to be a little hard to do. Okay, so you have to use a plumb bob to calibrate that, to make sure that you are over that particular spot. Plumb bobs give you that perfectly vertical line. Now you're looking at my forehead. Okay. So they used a tensioning guide to make sure that they were pulling with consistent tension. So it's hard for us to do it manually, even on short stretches, but pulling a steel tape and getting it to stretch can happen. What if it's a hot day? What happens to steel when it gets hot? Let's see. I mean, you could take just about anything. Elastic, waistband of your pants. You can always get a little bit of stretch out of it, right? Even with steel. Probably not as much as your pants after Thanksgiving. Okay. So make sure that it's level. Make sure that you have appropriate and consistent tension on it so that it doesn't sag, but also so you're not overstretching it. Okay. Use a plumb bob to make sure you are aligned vertically with your points. Take very good notes. If everybody keeps records as you go, then you have that to compare to. You have that precision. And hopefully your methods are giving you the accuracy so you can hit that target, right? Breaking the tape, they mentioned that. So if we're going 500 feet, I only have 100 feet of tape. So that was where you can kind of start to get off a little bit, and you have one homework problem that will address that. You get off a little bit after the first pin, and then you kind of overcorrect on the second pin to get to the third pin. Okay, so that will take you out of the way. All of a sudden, you're not measuring the straight line, you're measuring the hypotenuse. And it might only be a foot or two that you're off, but you're still off. Still a correction that needs to happen. Okay, calibration. I joked about calibrating the plumb bob. Gravity does that. Making sure that your tape reads correctly, your levels are in working condition. Make sure that you know your tools are in good shape. Okay? If you're using electronic equipment, make sure that that is calibrated and maintained. Okay. All right, and this is going to be the fun part. And I say that sarcastically because, oh boy. All right. All right, are we seeing the screen again?
Yes.
Okay, thank you. All right. Anybody have any questions? You guys doing all right? I took my watch off. Okay. I'll assume we're good. Let's see. 840. Steel taping. So if we are out and we are measuring using one of these tapes, whether it's steel or fiberglass, nylon, whatever the case may be, there are two types of tapes to be used. There's a cut tape, which requires subtraction to figure out where you are. There is an add tape, which is 90% of what people use these days. People don't use cut tapes anymore. What happens is, and what they were describing in the video, is that we take it from the nearest whole foot. And we either, here on this cut tape, we get the rear tape man to go to the nearest whole foot. And then from that point of, from 0 out to our measuring point where our plumb bob is dropped, then we subtract that amount. So there's always that little area at the beginning of the tape, at the head of the tape, right, that has those calibrations on it, that has those finer details instead of whole foot increments. Okay, you'll see the more defined, the bigger breakdowns that we're used to. An add tape, just the way it sounds, as opposed to a cut tape, we're going to add. That's why the tick marks are to the right of the 0 instead of to the left. So you always go to the nearest whole foot and then use your add or your cut tape. So your tail person, your rear tape man, is always holding it on the nearest whole foot. The lead tape man, the head tape man, is the one doing the math. That's who has to read the finer scales. Okay. How to calibrate a steel tape. So we mentioned calibrations. I don't like calling them calibrations. I use corrections. Okay. So we're used to making these corrections. Due to length, temperature, pull. Am I pulling too hard? Not enough. Is the tape sagging? What's the temperature? The ambient temperature. Is it 110 degrees? Is it 35 degrees? The properties of the material will play an impact. So we have all these different variables that we use. Okay, and you'll use these in your field books, in your notebooks. Length, L, typically 100 because we use 100-foot tapes. So the correction due to length, C sub L, based on this factor, is our standard length minus our tape length divided by our tape length multiplied by the measured length. So if we are missing some material off of our tape, that's how we would do a correction for length. Okay. Due to temperature, the coefficient of thermal expansion. Never thought I'd hear that again. Okay. We need to take what the normal temperature is. We need to take the difference between that and our current temperature. We need to use our coefficient of thermal expansion multiplied by our measured length, and that is the correction necessary due to temperature variations. Right. Due to pull, we have the cross-sectional area of the tape. Not real big. It's pretty little, okay? But we're dividing by that, so that could get kind of big. How hard are we pulling? Is the pulling going to change our length? Well, it depends on our material. Here we've got the modulus of elasticity of steel. If we're actually using a steel tape, this is a good correction to use. If we're using a regular nylon or fiberglass tape, that's going to have a different modulus of elasticity. So we have to look at the materials we're using. We might have to go look that up. Due to sag, right? If there's just two of us out there, we're pulling on this and it's hot. So we've got a temperature correction, we've got a correction for sag. You can only pull so hard before you start stretching the tape, trying to get the sag out of the middle, right? Trying to get that divot out. So we have a formula according to that, and that is a negative number, okay? Our adjusted length. What is the actual length? So what would be, out of all of this, what would be our direct measurement? Our measured length. What did we actually go out and record in the field? So how many times did we have to break the tape? How many different hundreds did we have? There's factors associated with each one of those. Our indirect value is then going to be what's called the adjusted length. Because we didn't measure the adjusted length, we had to calculate it, okay? So we went through that pretty quick because I'm running short on time tonight. We don't have a whole lot more to go through. But did that make sense? You're going to cover a lot of this in lab.
Yeah, it was a good rundown because I've been curious on how to do some of that stuff. So
And, you know, if we were actually sitting in class right now, everyone would have their, you know, partnered up. You'd have your tapes, you'd be playing with these things, you'd have them in your hands, you'd be feeling how heavy this is. And I got to be careful because I'm a klutz and I will take out my iPad and a couple monitors while I'm at it. You know, we're really missing the hands-on part of it. I did hear from Kyle, the intention is that October 17th and 24th will be the live and in-person hands-on portion. That's what we're going to work towards, getting you physical contact with the equipment. So keep your fingers crossed on that. Joanne's going to submit the paperwork to let it happen. We will definitely talk more about that as time goes on. We've got a little bit of time to cover that. So I'm going to end up posting all of this. This is a great slide, something to hang on to. It's also probably going to be some formulas that you want to write into your field book. You're probably going to want to have that stuff pretty handy. The different correction factors, the different variables. How do we reference each of those pieces of data? Okay. Good Lord. Keep doing that. Let me get rid of that. All right. So I didn't clean up this slide. There are certain givens, right? So the standard temperature we're going to assume is 68 degrees Fahrenheit. Pretty typical for Central Coast California. Not too terribly variable. If you've got a warm day, you get those down there sometimes. Maybe you measure it out at 95 degrees. So when we calibrated this tape, we took it out, it was a nice cool day, that's our standard, we've measured it out, we've tested it, we know it's 100 feet when we are, actually it is 100.014 feet at 68 degrees, 12 pounds of pressure, okay? 12 pounds of pull. We pull a little bit harder. We have kind of a warm day and we are measuring this almost 7 times over. We're leapfrogging it, right? Zigzagging back and forth. Other factors that we're going into, right? Yes, Marcine, thank you for clarifying that. We will still be doing things safely in the times of the COVID. So it's going to be broken into 2 dates, 2 different labs, same lab, just different dates. So we can get everybody in safely and spread out. Okay. All right, introduction to surveying. Thought this whole thing was introduction to surveying. However, different methods of surveying, different methods of covering information, right? Let's see, all right. So I'm running a little bit short on time tonight. This is covered mostly in the reading. Different ways we can go about taking these measurements. We can do it from the air. We actually have a lot of records of aerial surveys, right, where we've got marks on the ground. And a lot of times that was how we got our topographic maps, our originals, right? Ground surveying, boots on the ground. Our feet are physically in the area. We use GPS. 20 years ago, we had GPS systems hooked to our vehicles and you had to push a button every time you wanted it to record. And if the satellites weren't perfectly aligned, you had no signal and you just spent a day for nothing, right? Sitting out on a job site. Field surveying, that is majority of what we're going to be covering in this class, okay? How do we do it with our hands, with our bodies, physically out on the site? without actually physically going out to the site. So this is going to be a challenge. We'll get through it. All right. Aerial surveys. LiDAR is so new. Really cool stuff. It can see through the trees. It can penetrate through that. Earlier methods of aerial surveying, if there were dense grasses, I mean, if it had been a wheat field or a hay field, and there was still all this grass all over it, tall weeds, that could throw off the survey. We may not have the right elevations. Your elevations could be wrong. So there were detriments to the validity and the accuracy of the aerial survey. Now we can go through, we can see through that. We can get down to more solid ground, and we can get these much more detailed, much more intricate maps. Okay. Property surveys. Olga, I think that was you who said, you know, what's the size of my property?
Yeah.
What's the area, right?
Yeah.
Here we have an irregularly shaped property line. Okay, what are we looking at? And what do we have? Sheridan Road. But this tells us what our boundaries are, and that's the information we're looking for. Okay. Topographic surveys. Kenny, I wasn't able to get that open or downloaded, but I will bring it up next time. We'll definitely take a look. Kenny shared with me a PDF version of a topo map of Cabrillo College. So we can get in there and look and see what are we actually dealing with. This one, I really wanted to have some fun with this particular slide, but again, I ran out of time. Do I have flat ground? Do I have a hillside? Do I have a cliff? Do I have a pit? What am I looking at? What is the earth doing in 2 dimensions? Except we're 3-dimensional. So trying to figure out, what do I need to do to make this work? What I wanted to do was get 2 topos, and maybe we'll still do it, but where you see the congregation of a whole bunch of lines really close together, that's where it starts to get steep. So that's what we need to figure out is, am I talking about a hilltop or a tabletop? Where do you want to build your house? Hilltop? Tabletop. Tabletop's going to be a nice, easy way to go. Okay. So if we zoom into the quarry aspect of it, see, the closer these lines get together, the steeper we're talking. The further apart they get. So this is these lines, whoops, whoopsie. These are every 2 feet. Okay. So I have to go this far to go 2 feet in vertical elevation, as opposed to over here where I only have to go that far to get 2 feet in elevation. So the topo maps tell us really a lot. Those are hugely detailed. Our good old standard highway plans, okay, route surveys, they'd be called. What's our alignment? What is the topography that we're dealing with on those? We still have the topographic details, but where are the other physical features? What are the other details that we get? Construction surveys. Where is the point? And am I going to remove material? Do I need to add material? Am I in the right location? So that's the information that we need there. What's the data? Okay, so that's more areas of surveying that we get into. As-built surveys. there, if we go out into the field and we go to build a system, right? Storm drain, sewer, water, a building, whatever the case may be. If there's something in the way, if there's a big transmission pipe going right through the middle of the site, we're going to have to work around that. So we want to be sure we mark where that existing line is and keep track of it, because it wasn't on the plans to begin with. Somebody didn't even know it was there. Okay, now we found it. Now we need to record it. But now we've had to move all this other stuff around the side of it. So it doesn't look like what the engineer originally intended. So that rerouting, the next time somebody goes out and they need to find out, where is that sewer clean out next to your house? You want that as-built survey to be as accurate as possible so they can find it. You've seen the commercials for septic tank cleaning. And they talk about, well, the only time you ever have to go find a septic tank is pouring down rain, middle of the night. So you want to know, you want a map of where that actually went in. If you think it went in on the northeast corner of your house, only they started hitting boulders when they were digging and they moved it to the northwest corner, that's really going to get messy. As-built surveys are incredibly critical in the construction industry. And unfortunately, they are given about as much attention as a goldfish. Kind of sucks. All right. Wow. That ended right at 9. So we didn't get deep into what we talked about from the first week. Professional licensing, surveyors, engineers, the difference between the two professions, trigonometry and geometry review. You guys took the quiz. We'll go through, we'll get those graded, get some feedback to you just so we're all on the same page. What else did we talk about? We talked about significant digits. We talked about conversions. We did our quiz. I'll give you guys about 5-10 minutes next time before we jump right into the quiz. I got started kind of early. I was so excited, actually. We talked about distance measuring, right? Horizontal, vertical, slope, angles. That's the majority of it. We talked about the various corrections needed if you're dealing with steel tape. Literally, the metal steel. Or we can look at it differently if we're using a different material, right? Introduction to surveying. The types of surveys, the methods of surveys. Why do we survey? What do we get from it? What do we need? Some of it is very preliminary. It's the beginning of the job. Some of it, like the as-built, it's the very end of the job. Okay. And we have no Kyle, so not much to do on the taping traverse, but essentially what you've seen in that video today from the UCLA students, that's pretty much what you're going to be covering. Okay. Very, very similar to that. And lab number 1, which you're going to be doing on your own, is the pacing lab. Brandon, hold tight. We'll get that sorted out. Angel, you are now officially added to the class, I believe. Yay, nay. Anybody have any questions so far? Anything you want to review? Okay.
Actually,
Next
well,
slide. Yeah.
sorry. Well, if it's okay, I would like to review just one of the questions from the quiz, and there was an equation I used. What was it? The solution for oblique triangles, where you're given all the sides of the triangle, and you need to find at least one of the angles. Right.
Which one was that?
I think question number 3.
Yeah, question 3, you had all the sides,
Yeah.
and you were asked to find 2 of the angles.
right.
Okay.
And so my only question is, I followed through the whole steps, and it's pretty straightforward. But when I got to the sine 1/2 A, for some reason I got confused on what to do there. It's sine 1/2 A equals whatever value you put in for that equation. And so I took the inverse of sine, but I think I divided by 2, and I think I was supposed to instead multiply that thing by 2 in order to get the correct angle. But I'm not sure if I'm just mistaking.
Now, anybody else can chime in here. I didn't end up with a sine equation.
Okay.
Are you talking about finding angle A or angle B?
Angle A, I believe.
Angle A, you're going to want to use the law of cosines to find that angle.
Right.
Right.
Okay. Yeah. Thank you. That actually makes more sense than what I was looking at. So, all right. Well, just something to review.
Okay.
So thank you. Thank you very much.
You're welcome. You're welcome.
Yeah.
So Marcine just posted that she will be having her office hours tomorrow and Wednesday, 5 p.m. to 6 p.m. Take advantage of it. She's taken this class more recently than me. Okay. My office hours, I have posted those, finally got my act together. So I will be online and available Wednesday afternoons, 12:30 to 2:30. So part of that is I'm volunteering in the STEM Center, and part of that is my office hours, but use any part of that for your questions whatsoever. Next class is next Monday. Homework assignment has been posted to Canvas. Just like this time, it'll be due at the beginning of next class. We will have another quiz, pretty much on what we covered today. The slide deck will be posted. Give me a little time. There's some things I want to clean up on it, but we will get that posted. We will get the recording posted as well. And there's a reading assignment. So be sure and take note of that. There was something else I was going to mention. Oh, the quiz. Yes, as soon as I go through those, the quizzes and the homeworks, I will definitely share the solutions with everybody. Okay. And we will be more than happy to spend a little bit of time at the beginning of next session reviewing anything that you guys have questions on. So I will get that information back to you so you have time to digest it, review it, develop your arguments for why you're right and I'm wrong. Okay. I'll stick around for a little bit, but other than that, that's our 3 hours. The next hour is intended for you to catch up on some of your lab work. Ordinarily, Kyle would be here and you guys might have a little bit of a discussion, but mostly you're on your own.
Well, thank you. I had a quick, well, not a quick question about the quiz. Just wanted to let you know that last semester I had a teacher who had it all on paper, and then he had us email it. So that's what I was starting to do, and then I realized, oh, it's much easier. It's on Canvas and everything. So you'll be uploading it on files and also on the Canvas module as well.
Yes.
Okay.
Yeah.
That actually helps a lot because I like doing it on paper and everything. So, all right, cool.
Okay.
Thank you.
You're very welcome. And you guys, some of you have been emailing me. Did I upload the quiz? Oh, crap. All right, well, I'll take a look. Thanks, John. I think that's it.
So I had a quick question.
Yeah, please.
Uh, do we meet for lab at a specific time?
Ordinarily, if there's going to be a discussion portion of the lab, it would take place right after this. So from 9 to 10 on Monday nights. But I believe, and Marcine, if you want to jump in, each lab is going to be a standalone module. So everything will be posted to Canvas. You can pretty much do it at your own pace.
Okay.
I believe he mentioned that there will be some synchronous labs, but he'll give a heads up, and I'm sure it'll be listed within the module. But for the most part, the lab prep will be on your own time and schedule.
Thanks.
Yeah, so on the 21st, so next week, Kyle will join us for a little while during class and prep you for the lab that would theoretically take place on the 26th. So he'll explain what's going to happen, point out the videos that are necessary, the equipment that we might need, and get you ready for the upcoming lab. But these first two are a little bit more self-explanatory than any labs coming up. Does that help?
Yeah.
Okay.
Yeah, thanks.
Okay.
What's up, Sarah?
Brandon, what's
Brandon.
happening?
I don't know.
All right.
So what WebAdvisor is now telling me as of today, like yesterday and this morning, it was saying something different. Now it says in blue writing, authorized for ad, use register now to complete registration, but there's no register now button. And I looked through the help stuff that WebAdvisor has in the Cabrillo website and I can't find anything. It just like brings me back to my register page. But there's no blue button that says register.
Okay, I have no clue.
Me neither. And getting on the Canvas would really help so I could do like the
Yeah,
work.
yeah,
and,
we need.
because the online textbook's there too. And
So let's see. Marcine, do you have any experience with a late ad? Have you ever added anything late?
Luckily, I haven't had to deal with that, and I know it's more difficult now that you can't. Now it's all online, but I don't know who you would even contact about that, but possibly I might ask a counselor, because I know that there are services where they can walk you through the WebAdvisor process. Because I've heard this happen to some other person too, and I think they figured it out, but I have no idea what they did.
There was, where did she go? Kathleen. All right.
Is it not just the ad code provided by Sarah? Or
what it was at first, and then that disappeared, and now it just says authorized for ad, use register now, and there's no register now button.
So what happened was, between my ad authorization for you and you self-enrolling, we missed the deadline. So that's why we're struggling to get you caught up here. You saw the CabrilloInstructure.com enroll?
I did, and I checked that out, that link you sent.
Yeah.
And I couldn't really find anything there.
All right. And it sucks because there's nobody's office you can just march down to
Yeah.
and get it sorted out. Let me